Imagine stepping into a capsule on a launch pad in Florida, knowing that if everything goes right, you will not see Earth again with your own eyes for over a decade. Not months, not years. A decade at minimum. Somewhere out past the orbit of Neptune, 4 billion miles from home, there's a small icy world with mountains of frozen nitrogen and a heart. Shaped glacier the size of Texas. We have already sent a robot there. It took 9.5 years just to fly past. The question tonight is different and much harder. Could a human being make that same trip, survive on the surface long enough to matter, and come home alive? That question sounds simple. It isn't, and the answer depends on physics we've already tested, engineering we haven't finished building, and a version of the human body that has never been asked to survive what a Pluto mission would demand. Let's start with what we actually know. In January 2006, NASA launched a piano-sized robotic probe called New Horizons from Cape Canaveral. It left Earth faster than any spacecraft in history, roughly 36,000 miles per hour at launch, fast enough to leave low Earth orbit and never look back. Even at that speed, boosted further by a gravity assist from Jupiter in 2007, New Horizons needed 9 years and 5 months to reach Pluto. When it finally shot past the dwarf planet in July 2015, it was still moving so fast, over 30,000 miles per hour, that it had no way to slow down and enter orbit. It simply flew through the system, cameras firing for a few frantic hours, then kept going. Slowing down enough to stop at Pluto would have required, according to the mission's own engineers, more than 1,000 times the fuel the spacecraft actually carried. So New Horizons never stopped. It couldn't afford to. That detail matters more than almost anything else in this story. A flyby and a landing are two completely different missions. And a human mission is a third thing entirely, because unlike a camera, a person has to eat, breathe, sleep, and survive the trip back. So picture the scale for a moment. Earth sits about 93 million miles from the sun. Astronomers use that distance, called an astronomical unit, as their yardstick for the solar system. Pluto, at its closest, sits roughly 30 times farther out than that. New Horizons covered that entire span, nearly 3 billion miles, averaging about 4 astronomical units of distance every year. To put that in a more human frame, if driving from New York to Los Angeles represented the distance from Earth to the Moon, the trip to Pluto on that same scale would be like driving around the planet Earth more than 400 times. That is the gap a human crew would need to close, then close again on the way home. Here's the first real obstacle: fuel. Chemical rockets, the kind that have launched every crewed mission in history from Apollo to the International Space Station, work by burning propellant and shooting it out the back. They're powerful for getting off the ground, but wildly inefficient for a 9-year cruise. To accelerate a crewed spacecraft heavy enough to keep humans alive, then decelerate it at Pluto, then accelerate it again for the trip home, then decelerate one final time at Earth, using only chemical propulsion, the fuel requirement grows so large that the ship would mostly be fuel tank. Engineers sometimes describe this as the tyranny of the rocket equation. Every extra pound of fuel needs its own fuel to carry it, which needs its own fuel, and the numbers spiral upward until a chemical-only Pluto round trip becomes close to physically absurd to build. That's why any serious version of this mission depends on a different kind of engine. For decades, NASA and other space agencies have studied nuclear thermal propulsion, a design where a nuclear reactor heats a propellant like hydrogen until it expands and blasts out of a nozzle, producing far more thrust per pound of fuel than chemical rockets. NASA and DARPA have been developing exactly this kind of engine in recent years, aiming for a demonstration in Earth orbit. Not because anyone announced a Pluto mission, but because faster, more efficient propulsion is the baseline requirement for any serious deep space human spaceflight, Mars included. A nuclear thermal or nuclear electric engine wouldn't make a Pluto mission easy, it would make it thinkable. Even with better propulsion, though, speed creates its own problem: stopping. New Horizons never had to stop. A human crew would. Arriving at Pluto at flyby speed and doing nothing but taking pictures defeats the purpose of sending people at all. To actually go into orbit or land, the spacecraft needs to shed the same enormous velocity it built up getting there, which means carrying enough propulsion capacity to decelerate a much heavier vehicle than any robotic probe. Then, after the mission at Pluto is complete, it needs to do the entire process in reverse, accelerate away from Pluto's incredibly weak gravity, cruise home for years, and slow down again to be safely captured by Earth. Every stage of that journey demands propellant, and every gram of extra propellant makes the ship heavier, which demands more propellant still. There's a second option engineers sometimes raise instead of a full stop: send humans on a flyby, the same maneuver New Horizons performed, just with people aboard instead of cameras. It sounds like a shortcut, and in fuel terms it is, but a human flyby solves almost nothing that matters. The entire justification for sending a person instead of a probe is judgment, adaptability, the ability to study something up close and change plans in real time. A crew screaming past Pluto at 30,000 miles per hour with only a few hours of usable observation time before the planet shrinks back into the dark gains almost nothing a robot couldn't already provide, while still absorbing nearly a decade of radiation and isolation to get there. If the mission is worth doing with people at all, it's worth doing as a real arrival, which means it's worth solving the harder problem of stopping. That's the mechanical half of the problem. The other half is the human body. Radiation is the quiet threat on a mission like this. Beyond the protection of Earth's magnetic field, astronauts are exposed to galactic cosmic rays, high-energy particles from outside the solar system that chemical shielding struggles to block completely. NASA's career radiation limits for astronauts are based on missions lasting months, not the better part of a decade. A round trip to Pluto, even using faster nuclear propulsion, would likely take years longer than any human has ever spent in space, which means mission. Planners would need either much heavier shielding, which adds mass and cost, or an entirely different approach to limiting exposure, none of which currently exists as a finished, flight-ready system. There's also the simple matter of keeping people fed, watered, and breathing for the better part of a decade with no chance of resupply. Every mission flown so far, including the International Space Station, depends on regular cargo shipments from Earth to top up food, spare parts, and consumables. A Pluto mission couldn't do that. It would need what engineers call a closed-loop life support system, one that recycles air and water with almost no loss and grows or preserves enough food to last the entire round trip, sealed inside the ship the whole way. Current life support technology recycles a high percentage of water and oxygen on the space station today, but high percentage isn't good enough for a 9 or 10-year loop. Even a small daily loss, multiplied across thousands of days, adds up to a supply problem no cargo rocket could fix once the crew is past Jupiter. Then there's the body itself, in freefall for years at a time. Long-duration missions on the International Space Station, some lasting close to a year, have already shown that extended weightlessness weakens bone density, shifts fluids in the body, and affects eyesight in ways researchers still don't fully understand. Stretch that exposure from months to nearly a decade, and the physiological toll compounds. A realistic Pluto mission would almost certainly need some form of artificial gravity, likely generated by spinning a section of the spacecraft. An idea studied since the earliest years of spaceflight, but never built for a real mission. And then there's the mind. 6 to 10 years is longer than most people spend in a single job, a single relationship, a single home. A Pluto crew would live inside a metal hull with the same handful of people for the entire journey, with communication delays to Earth stretching to over 9 hours each way once they reached Pluto's distance. Exactly what New Horizons' own engineers experienced when they waited 9 tense hours just to learn whether their flyby had succeeded. A conversation with home wouldn't be a conversation anymore. It would be a message and a very long wait. So where does that leave the mission physically? There's a useful comparison here, if only as a boundary marker. Voyager 1, launched in 1977, is now the most distant human-made object in existence, well over 100 astronomical units from the Sun, and still climbing, decades after it passed Pluto's distance and kept going. Voyager never had to protect a crew, feed anyone, or turn around and come home. Once it left, it simply kept traveling outward forever. A human. Pluto mission asks for something Voyager was never built to do, and New Horizons wasn't either. Not just reaching that distance, but stopping there, and then reversing the entire journey. Every spacecraft humanity has ever sent that far has been a one-way trip, or a flyby. Nothing built has ever done what a returning human crew would need to do twice. Layer these constraints together, and a picture starts to form. The propulsion problem is solvable in principle. Nuclear thermal and nuclear electric systems already exist in prototype and testing form, but not yet built at the scale or reliability needed for a crewed, multi-year deep space mission. The radiation problem is understood and outlined, but unsolved in practice for missions this long. The biological and psychological problems are being actively studied through Mars mission research and space station experience, but nobody has tested a human body, or a human mind, against a full decade of isolation and reduced gravity. None of that means impossible. It means not yet. It also means the mission wouldn't be attempted as a single leap. Every major step outward in human spaceflight history has been staged. Mercury before Gemini, Gemini before Apollo, Apollo before the space station before anything resembling a plan to send people toward Mars. Each stage tested one new capability, radiation exposure, spacewalks, docking, long-duration living, before betting a crew's life on the next one. A Pluto mission fits at the far end of that same ladder. Not as an isolated stunt, but as the last rung after everything closer has already been proven. Consider what not yet actually looks like on a timeline. Serious nuclear propulsion demonstrations are targeted for the coming years, aimed initially at Earth orbit and eventually Mars-class missions. Mars itself, a much shorter and far less radiation-intensive trip, remains the primary human deep space goal for the coming decades, a Pluto mission. Would logically come after that, once propulsion, shielding, and long-duration life support have all been proven on a shorter, survivable trip first. Engineers rarely leap straight from low Earth orbit to the edge of the solar system. They build the capability in stages, the way Apollo built toward the moon. If humans did eventually attempt it, the mission almost certainly wouldn't look like the crude capsules of today. Picture something closer to a small, self-contained station, a rotating section for gravity, heavy radiation shielding wrapped around a central habitat, a nuclear reactor powering both propulsion and daily life support, and enough redundancy in every system to survive a decade without a resupply ship, because no rescue mission could reach a crew that far out in any useful time frame. If something failed badly near Pluto, help wouldn't just be far away. It would be, for all practical purposes, unreachable. That's the honest shape of the answer. Reaching Pluto and returning is not blocked by any law of physics. The distance is enormous but finite. The propulsion physics for a faster, more efficient engine already exists in early testing. What's missing is the finished hardware, tested at the scale a real mission would need, plus solutions to radiation exposure and long-duration human survival that are still being worked out, mission by mission, on far shorter trips closer to home. New Horizons proved something important 9 years into its own journey. Humanity is capable of building a machine that can cross the solar system, survive the crossing, and still function well enough to make history in a matter of hours. What it also proved, in the fuel calculations engineers made before launch, is that stopping is a completely different challenge than passing through. A human crew would need to stop, not once, but twice, arriving and returning, while keeping people alive for every mile in between. So could humans actually reach Pluto and make it back to Earth? With propulsion systems currently in early testing, radiation shielding still being refined, and life support that has never been proven beyond about a year in space, the honest answer is, not with what exists today, but not because the destination is impossible. It's because the mission would ask more of the human body and of our machines than any spaceflight in. History has ever asked before. The distance was never really the hardest part. Surviving it, twice, is. If you had to spend 9 years in a metal box to see something no human has ever seen with their own eyes, would you go? Tell me in the comments, and I'll see you in the next one.